Imagine you are driving down the highway at like 70 miles an hour.
Okay, I'm picturing it.
Right. And deep inside your car's engine, there is this tiny, just perfectly engineered metal shaft. It's, maybe the thickness of a toothpick.
Yeah, it's super small.
Exactly. But it is spinning thousands of times a minute, just metering out fuel with absolute perfection to keep you safe and moving.
Right. Which is incredible when you stop to think about
It
it.
really is. Or picture the intricate little titanium screws holding a medical implant together inside someone's body. We basically walk through our days completely surrounded by this invisible world of microscopic manufacturing.
We do, yeah. And we rarely ever think about it.
Never. But those perfectly engineered tiny parts are literally the silent foundation of modern life. I mean, they keep our medical devices running, our vehicles safe, and our electronics connected.
Absolutely.
So today, we are taking a deep dive into the hidden mechanics of exactly how that invisible world gets built.
And it truly is a hidden ecosystem.
Yeah.
I mean, the reason we don't think about it is because we just assume making something small is, exactly like making something big, just scaled down.
Right, like you just use a smaller saw or something.
Yeah, exactly. But when you shrink mechanical parts down to, say, the width of a matchstick, the actual laws of physics change.
Wow, really?
Oh, for sure. The rules of how you cut and shape metal have to be completely rewritten at that scale.
Well, our mission for this deep dive is to explore one of those brilliant rewrites. We are unpacking the mechanics, the economics, and honestly, the sheer engineering wizardry of a specific manufacturing marvel known as the Dual-Spindle Swiss-type lathe.
Which is quite a name.
It is, yeah.
Yeah.
No,
yeah.
I know that name sounds incredibly niche to anyone who doesn't, spend their weekends reading industrial catalogs.
It is definitely a mouthful.
Yeah.
But you don't really need to be a machinist to appreciate what this is.
Yeah.
What we are really looking at here is a masterclass in solving complex physical problems. It's a brilliant study in elegant design, the integration of multiple processes, and ultimately, the complete elimination of human error from the factory floor.
Okay, let's unpack this, because before we get into the dual part of the dual spindle lathe, we really have to frame the core problem here.
Right, the reason it exists in the first place.
Exactly. Making small, long, detailed shaft parts is an absolute nightmare if you are using ordinary machining. So why is it so incredibly difficult to just cut a tiny piece of metal?
Well, to understand the difficulty, you really have to visualize what happens when you cut metal on a standard traditional lathe.
Okay.
In ordinary turning, you take a piece of raw metal, say like a long steel rod, and you clamp it tightly at one end.
Just one end.
Right, and the rest of the rod just sort of sticks out into the air. Then you bring a hardened cutting tool in from the side, and you just press it against that spinning rod to carve away the material.
Okay, I can picture that.
But the fatal flaw here is overhang.
Right, because the material is just hanging out there in empty space with no support on the far end.
Exactly, which is a massive physical obstacle.
Yeah.
I mean, if the part you are making is long and thin, and you press a sharp, heavy tool against it, the metal doesn't just sit there perfectly rigid and take it.
It's going to move.
It flexes.
Mm.
It bends away from the tool.
Yeah.
And in engineering, this is called deflection.
Deflection, okay.
Yeah, and in a traditional setup, this tiny microscopic bending leads to just an absolute cascade of problems.
Like what?
Well, you get errors in the dimensions, you get a terrible chattering surface finish, ruined parts.
Basically a bin full of expensive scrap metal.
Exactly. And add in the fact that to finish different sides of a part, a human operator often has to physically unclamp it, move it around, and reclamp it.
Oh, wow.
Yeah, so your output becomes completely unstable.
So the core physical obstacle is just bending, the metal flexing under the intense pressure of the cut.
That's it.
To make this visceral for you listening, imagine trying to carve a block of cheese, but the cheese is attached to the end of a really long, thin stick.
Right, great analogy.
As you press the knife down to take a slice, the stick just bends away from the knife, You can't get any leverage, so your cut is totally uneven.
Yeah, it's a mess.
But if you hold the stick right next to where you're cutting, your hand acts as a guide. Suddenly, you get a perfect, uniform slice every single time.
That captures the physics perfectly. And that exact principle is the defining genius of the Swiss-type solution.
Okay, how so?
Well, to stop the deflection, they introduced something called a guide bushing, combined with a sliding headstock.
A guide bushing?
Right. So instead of clamping the metal in place and dragging a cutting tool up and down its length, the machine does the exact opposite.
Wait, what do you mean?
The main spindle holds the back of the metal bar and physically pushes it through the guide bushing.
Oh, I see. So the raw material is actually sliding forward into the cutting zone rather than the tool traveling down the material.
Yes, exactly. And that changes everything because the guide bushing acts like a tight, supportive collar around the metal.
Right.
And the cutting tool is locked in place barely a millimeter away from that collar.
So the cutting point stays incredibly close to the support point no matter how long the final part is going to be.
Exactly. By designing it this way, you are completely suppressing that bending. You neutralize the deflection entirely.
That is wild.
Yeah, and by solving that microscopic flex, you instantly remove the biggest risk for error when making slender shaft parts. I mean, the rigidity isn't added on later. It is literally baked right into the fundamental design of the machine.
It is incredibly elegant. You don't, try to correct the bending. You just design a system where bending is physically impossible.
Exactly.
But that brings us to the next massive hurdle. Let's say we've successfully machined the intricate front half of this tiny part without any deflection. It looks great, but it is still physically attached to the long bar of raw material coming through the machine. We face a totally new problem. How do you cut it off and finish the backside of this tiny part without undoing all that incredible precision we just achieved?
Which leads us directly to the magic of the dual spindles.
Here we go.
Yeah. In traditional manufacturing, finishing the backside of a part is where everything goes wrong.
Why is that?
Usually you cut the part off, it drops into a bucket, and a human worker has to actually stop a second machine, pick the part out of the bucket, physically flip it around, and clamp it back into a new chuck for a second operation.
And doing that manually is an absolute precision killer. I mean, you take this perfect piece, and the second a human hand clamps it again, the center line shifts.
Exactly.
It creates a defect called runout, right?
Wow.
Which destroys the consistency from part to part.
Yes. Runout is the enemy here.
For you listening, think of runout like a wobbly bicycle tire. The rim itself might be perfectly round, but if it isn't mounted perfectly centered on the axle, it wobbles as it spins.
Great way to put it.
You are basically relying on a human to put this microscopic part back perfectly centered without a single speck of dust throwing it off every single time.
And at the microscopic level, human hands and manual chucks are just not precise enough for that.
Right.
So the dual spindle solution completely changes the game.
How does it work?
While the main spindle is pushing the material through the guide bushing and finishing all those front side features, turning the diameters, milling flat spots, drilling holes, the second spindle, which is called the sub-spindle, is just waiting in the wings.
So it's like a perfectly timed relay race.
A relay race with zero drop batons. When the front of the part is done, the sub-spindle actually moves in on its own. It docks with the part while it's still attached to the main bar and grips the tail end of it.
While it's still attached.
Yep. Only then is the part cut off. The sub-spindle then pulls back into its own cutting zone and finishes the rear features of the part. Yeah, there is no manual flipping, no dropping it in a bucket. All the turning, milling, drilling, boring, tapping, cutting off, and even the final unloading of the finished part happens in one continuous, uninterrupted, automated cycle.
But wait, I have to ask. If they are passing this tiny, delicate part back and forth between two distinct mechanical spindles and the machine is running at incredibly high speeds, how do they not just crash into each other? Or, crush the part?
What's fascinating here is the concept of spindle docking. This isn't just one clamp roughly grabbing a piece of metal from another. The machine is performing micron-level transfer control.
Micron level.
Yeah. Before the sub-spindle even touches the part, its computer synchronizes its exact rotation speed with the main spindle.
Oh, wow.
They match the RPM, the phase, and the exact rotational position. They are spinning together in perfect synchronized harmony before the handoff even happens.
So it's like two cars driving side by side at 100 miles an hour, passing a glass of water between the windows without spilling a single drop.
That is a great way to visualize it. And because the part never actually leaves a spindle's grip during the entire transfer process, you completely eliminate the accumulated positioning error that happens when a human worker gets involved.
Right, because it never loses its reference point.
Exactly. The machining reference point stays perfectly intact. And because of this flawless handoff, when they are making complex shaft parts, the concentricity, which is how perfectly centered the front features are to the back features, can be kept within a staggering 0.01 millimeters.
0.01 millimeters.
Yes.
just to put that in perspective for a second, a standard piece of printer paper is about 0.1 millimeters thick. We are talking about a tenth of the thickness of a sheet of paper.
It's tiny.
It is barely a suggestion of a measurement to the human eye. And because this machine transfers the part seamlessly, entirely without human hands, it completely upends the math on how fast manufacturing can actually happen.
It really does.
So we're moving from the physical mechanics of the machine to massive time savings and economics now.
Yeah, and the efficiency gains are truly disruptive to traditional factory models.
Yeah.
We are talking about reducing the single-piece machining time by 40 to 50% right off the bat.
Wow.
And when you compare it to standard single-spindle CNC lathes, the overall efficiency improves by 50 to 100%.
And looking at mass production, the sources say capacity can hit 3 to 4 times higher.
Easily.
But wait, I have to push back on this a little bit.
Sure.
A 300 to 400% capacity increase just by adding a second spindle to the machine. I mean, that math feels incredibly inflated to me.
I can see why you think that.
Right. Are we really getting that much more output just by saving the, 5 or 10 seconds it takes a guy to open a door and flip a part around?
I completely understand the skepticism. It does sound exaggerated until you actually break down the hidden logistical losses in traditional manufacturing.
Okay, break it down for me.
You aren't just saving those 5 seconds of flipping. The massive time savings come from 3 distinct compounding areas. The first is parallel work. While that sub-spindle is safely in its own zone, finishing the back end of the part it just received, the main spindle doesn't just sit there waiting.
What does it do?
It immediately starts roughing out the front section of the next part on the raw bar.
Wait, really?
Yeah, they're literally cutting 2 different parts simultaneously inside the same enclosure.
Wait, so you have 2 separate machining operations happening inside one box at the exact same time?
Yes.
How does it manage the vibration of 2 cutting heads tearing into metal without ruining that microscopic tenth of a sheet of paper tolerance we just talked about?
That comes down to massive, heavy cast iron machine frames that just absorb kinetic energy, and of course, that guide bushing we discussed earlier.
Ah, the guide bushing again.
Right. The guide bushing locks the material so rigidly that the vibrations from one spindle don't travel through the machine and affect the other. That isolation eliminates massive amounts of idle time.
Okay, that makes sense. What's the second area?
The second reason for the speed increase is process integration. You are doing the work of several different distinct machines in one single setup.
Give me an example.
Think about a complex part, like a medical bone screw.
Okay.
Previously, you might turn the threads on a lathe. Then that whole batch gets put in a plastic pin. A worker walks it over to a milling machine to cut the flats for the screwdriver head.
Right, lots of moving around.
Exactly. Then they walk it to a drill press to put in a crosshole.
So it's not just the 5 seconds to flip it. It's the hour it sits in a bin waiting for the milling machine operator to come back from lunch.
Yeah.
It's the extra quality inspections required between every single one of those manual machine changes just to make sure the new operator clamped it right.
That is the real bottleneck. It's the work in progress waiting time, the dead time, the sheer logistics of moving metal around a factory floor.
Wow.
When you integrate all of that turning, milling, drilling, and tapping into one program cycle on one machine, those hidden losses just vanish entirely.
That's huge.
It is. In a production line, the time saved on logistics is often larger than the actual metal cutting time itself.
Okay, and the third reason?
Thirdly, you have automation.
Right, the automatic bar feeders. Because you don't feed these machines one little chunk of metal at a time, do you?
No, not at all. You load 12-foot-long bars of raw material into a mechanical feeder attached to the back, and it just continuously feeds the main spindle.
Just nonstop.
Exactly. And meanwhile, the sub-spindle gently unloads the finished parts onto a conveyor belt. A single operator can manage a whole row of these machines, and they can run all night with the lights out and minimal labor.
That is crazy.
When you combine parallel cutting, process integration, and that automation, your equipment utilization skyrockets. In well-planned mass production, these machines operate at over 85% utilization.
Which is practically unheard of.
Right, and that is where your 300 to 400% capacity explosion comes from.
Okay, that makes total sense when you factor in the death of all that factory floor dead time. I mean, the part never waits in line. But this brings up a really interesting paradox. Usually in manufacturing, or really anything in life, if you are moving incredibly fast and doing 5 complex jobs at the exact same time, speed comes at the cost of accuracy.
Usually, yes.
Right, like if you rush, you make mistakes.
Yeah,
Yet this machine seems to do the exact opposite. It's blindingly fast, but supposedly hyper accurate.
it is.
Surely there is a vulnerability in a system this tightly wound.
Well, there is always a vulnerability when you are pushing the physical limits of raw materials. But first, let's look at the actual numbers they're achieving, just to understand the scale of this precision.
Okay, let's hear them.
We are talking about dimensional accuracy around plus or minus zero point 0 to 1 millimeters to 0.005 millimeters.
Oh my goodness. Just to give you listening some mental context here, a standard human hair is about 0.07 millimeters thick. So we were talking about dimensional tolerances. They're just tiny, tiny fractions of a single human hair.
And in an ideal temperature-controlled conditions, they can push that to plus or minus 0.0008 millimeters.
That's absurd.
It gets better. The surface roughness can reach Ra 0.1 to 0.4 micrometers.
Okay, what does that mean in plain English?
To translate that, a Ra of 0.1 means the surface is essentially a mirror finish.
A mirror finish.
Yeah. It is completely smooth to the human touch, straight off the cutting tool with absolutely no extra polishing required. In mass production, they consistently hit IT5 to IT6 level tolerances.
Wait, I have to ask, what is an IT grade?
IT grades are international standards that measure manufacturing precision based on the overall size of the part.
Okay.
Hitting an IT5 on a production floor is incredibly difficult. Think of it like trying to parallel park a car at 50 miles an hour and getting it right down to the exact millimeter thousands of times in a row without a single scratch.
That is mind-boggling. How is the machine keeping its digital brain straight to manage that level of perfection while moving so violently fast?
It requires an incredibly high-end technological ecosystem. The machines utilize sophisticated dual-channel CNC systems,
Dual channel meaning?
meaning they have entirely separate computer processors controlling the main and sub-spindles simultaneously, so there is zero communication lag.
Wow, okay.
They also use high-resolution encoder feedback, which means sensors on the motors are constantly reporting their exact physical position back to the brain millions of times a second.
So it always knows exactly where it is.
Exactly. And crucially, they use active thermal compensation.
Thermal compensation. Because, of course, when you drag a sharp tool across spinning metal, it creates immense friction and heat.
A lot of heat.
And when metal gets hot, it expands.
It expands significantly at this scale. I mean, even a 1-degree shift in the ambient room temperature can cause the heavy iron frame of the machine, or the metal part itself, to expand by a few microns.
Oh, wow. Just from the room temperature.
Yeah. And the world of fractions of a hair, that expansion ruins the part.
Right.
So the machine has thermal sensors placed strategically all across its body. It literally calculates the heat expansion and adjusts its cutting paths in real time.
You're kidding.
No, it actually moves the tool a microscopic fraction of a millimeter to the left or right to compensate for the temperature change. It is actively fighting the laws of physics every single second it runs.
Here's where it gets really interesting to me. The machine is packed with dual-channel processors, micron-level encoders, and thermal sensors.
Right.
It is so mathematically perfect. But the biggest flaw, its Achilles heel, is actually the dumb raw material you feed into it.
That's exactly right.
If the long brass or steel bar you buy from the mill isn't perfectly round, the whole multi-million-dollar system just falls apart.
That is the ultimate irony of the Swiss-type lathe. Remember the guide bushing we talked about?
Yeah, the collar that holds the metal.
The absolute secret to its rigidity and success?
Right.
Well, the raw bar stock has to fly perfectly smoothly through that tight guide bushing to be supported.
Okay, I see where this is going.
If the bar diameter tolerance from the steel mill is pour-like, if it's slightly too thick or even slightly oval-shaped, it jams inside the bushing and stops the entire machine.
And if it's too thin?
If it's slightly too thin, it leaves a microscopic gap.
And if there's a gap between the metal and the bushing, the metal bends under pressure, the deflection comes back, and you lose all your precision.
Exactly. The bar diameter tolerance needs to be within a plus or minus 0.02 millimeters just to feed properly.
That's incredibly strict for raw material.
It is. Not to mention the bar has to be perfectly straight, otherwise it violently whips around inside the feeder.
Oh, that sounds dangerous.
Yeah. If we connect this to the bigger picture, it shows that true precision isn't just a machine. It's an entire interconnected ecosystem.
Right?
You have to have perfectly straight, perfectly sized raw materials. You need supreme tool sharpness. The cutting oil you use to cool the part has to be chemically stable. Even the air conditioning in the room matters.
It's all connected.
You cannot put cheap, poorly toleranced raw materials into a hyper-advanced system like this and expect medical-grade outputs. The machine can only be as perfect as the material it is asked to shape.
But hold on, if the guide bushing is so critical to holding the metal, what happens at the very end of the bar? Or like, what if you just want to make a really short part? Do you just waste a bunch of material because it physically can't reach all the way through the bushing to the cutting tool?
That's a great point, and it's exactly why machine builders have engineered guide bushingless operations.
Oh, they can take it out.
Yeah. For extreme precision on long, slender shafts, the fixed guide bushing is non-negotiable. But if you're making short, stubby parts, some modern machines allow you to physically remove the guide bushing and just run it like a traditional lathe.
Which saves the leftover material.
Exactly. This drastically reduces the length of wasted material left over at the end of the bar. It's really all about adapting the tool's ecosystem to the specific geometry of the part you are making.
Okay, so we've established the incredible speed, the dual spindle choreography, and the microscopic precision of these machines. But let's ground this.
Let's do it.
We need to look at where these tiny, perfect parts actually go, connecting these abstract metal chips directly to the daily life of everyone listening. Because these aren't just, display pieces, these are foundational components of modern society.
The application list is essentially a cross-section of advanced modern industries. We are talking about medical devices, new energy vehicles, aerospace components, consumer electronics, 5G communication infrastructure, and even high-end mechanical watches.
The sources outline some really vivid examples, too. Bone screws used in orthopedic surgery, the tiny titanium roots for dental implants,
All made on these machines.
the miniature sensor shafts inside your electric vehicle's braking system, valve spools, fiber optic ferrules, and miniature gears. If you have a dental implant in your jaw, or if you're holding a smartphone packed with tiny microconnectors, you are holding the physical manifestation of this exact machine's labor.
And the reason these specific parts require this specific machine goes right back to that process integration we discussed earlier.
Doing it all at once.
Yes, exactly. Take a miniature hydraulic valve spool for an airplane, or a tiny 5G antenna pin. These parts are highly complex. They are multi-sided. They need flat surfaces milled into them. They need cross holes drilled precisely through the center. And they might need tiny threaded holes, all on a part that is less than 10 millimeters in diameter.
And if you tried to manually move a 5mm part between 4 different machines, you'd probably crush it with a clamp or just drop it in the metal shavings just trying to move it.
Precisely why doing it all in one pass is mandatory. Avoiding handling damage is absolutely critical, especially on fragile parts under 10 millimeters.
Makes sense.
Doing it all in one continuous cycle improves the yield dramatically. You don't lose parts to the factory floor, and you don't ruin them with clumsy secondary clamping.
Wow.
This raises an important question, though. As our technology continues to get smaller and more complex, where does this actually leave manufacturing? We want tiny sensors in everything from our refrigerators to our shoes. We want electric vehicles to be lighter and more efficient. We demand 5G antennas to be smaller and more powerful.
It really seems like our reliance on this highly specific type of one setup machining is only going to grow exponentially.
Oh, absolutely.
The real value of the dual spindle Swiss lathe isn't just how ridiculously fast it spits out parts. Its real value is stable precision at scale.
Perfectly said.
It allows designers and engineers to dream up complex, multi-featured microparts on their computers, knowing there is actually a physical way to mass produce them reliably. It bridges the gap between a theoretical CAD drawing and millions of actual components out in the real world.
It takes the chaos, the waiting, and the human error of a multi-step factory floor and condenses it into one incredibly tight, thermally controlled, perfectly synchronized metal box.
It really is a paradigm shift. By keeping the cutting tool right next to the support to defeat deflection, and then letting 2 spindles dance in perfect automated parallel to finish the front and back seamlessly, it is literally a microfactory in a single machine cycle.
It really is.
But looking at all of this leaves me with one final thought, something for you listening to mull over today as you look at your phone or start your car.
What's that?
If we are already mass-producing parts with tolerances that are mere fractions of a human hair, holding concentricity to 0.01 millimeters, what happens in the next decade?
Right.
When the devices we demand become so incredibly microscopic that the physical parts required surpass even the physical limits of a metal cutting tool. At what point does traditional machining finally end and atomic-level printing have to begin?
That is the frontier.
Yeah.
And based on how fast things are shrinking, it is much closer than we think.
We will definitely have to save that topic for another deep dive. Thank you so much for joining us on this exploration into the invisible world of microscopic manufacturing. We'll catch you on the next one.